Look at the structural footprint of this building. By stripping away the concrete and steel, we isolate a pure mathematical perimeter. For a geometric shape to be classified as a regular polygon, it must satisfy two strict conditions. First, it must be equilateral. Every line segment enclosing the shape has the exact same length. Second, it must be equiangular. The internal angles where these sides meet are identical across the entire structure. These dual conditions of symmetry create a predictable internal architecture. That predictability allows us to calculate the total enclosed area of the shape. Regularity in geometry operates as a rigid set of rules. By understanding these rules, we determine the properties of infinitely complex, multi-sided structures. This diagram shows a regular hexagon, which will serve as our structural test subject. We label its vertices A through F. Because the side lengths and interior angles are uniform, we can expand a perfect circle inside the boundary. This inscribed circle touches the exact midpoint of all 6 sides. Similarly, we draw a second, larger circle around the outside of the shape. This circumscribed circle precisely intersects every outer vertex. Because of the polygon's strict uniformity, both the inscribed and circumscribed circles share the same center point. We designate this shared location as point Q. Point Q acts as the origin. Every internal dimension and structural measurement of the polygon is derived outward from this center point. We can clear away the circular guides to isolate the hexagon and its center. A line segment drawn straight from point Q to vertex A is a radius of the regular polygon. When this radius connects to a vertex, it bisects the polygon's interior angle into 2 equal halves. Drawing a second consecutive radius from the center to vertex B forms a new angle at point Q. This is the central angle. To find the measure of any central angle, you divide 360 degrees by n, representing the total number of sides. The radius length and the central angle work together to dictate exactly how a regular polygon distributes its vertices in space around the origin. Now we focus our attention on the space between the center point and the flat sides of the shape. A line segment drawn straight down from point Q to the bottom side of the polygon is called an apothem. By definition, an apothem intersects the side of the polygon at a perpendicular, 90-degree angle. Striking the boundary at this exact perpendicular angle bisects the side into 2 segments of equal length. Keep the functions of these 2 lines distinct. The radius targets the vertex, the apothem targets the side, and as a result, the apothem is always a shorter distance. The apothem is a defining structural variable. It represents the shortest path from the center point to the polygon's outer boundary. Squares and equilateral triangles belong to the regular polygon family. They obey all the same anatomical rules regarding centers, radii, and apothems. We will use a square to test how these internal measurements let us calculate total area. Suppose we have a square with an apothem measuring precisely 2 inches. We assign the total length of the bottom edge the variable s. The conventional, baseline formula for the area of a square is the side length squared. Because the apothem originates at the exact center of the shape, the full side length must be exactly twice the apothem. With an apothem of 2, the side length is 4. Squaring the side length of 4 gives us a total area of 16 square inches. While multiplying side lengths works for a simple square, that specific equation fails when applied to a pentagon or octagon. We require a mathematical tool that scales automatically. That tool is Theorem 8.3.1. This theorem states that the area of any regular polygon equals 1/2 the length of the apothem multiplied by the total perimeter of the shape. We test this by running our previous square through the theorem's equation. First, we calculate the perimeter. Our square has 4 equal sides measuring 4 inches each, giving us a total perimeter of 16. We insert those values into the theorem. Area equals 1/2 times the apothem of 2 times the perimeter of 16. 1/2 of 2 is 1. 1 multiplied by 16 yields an area of 16. This result matches our baseline calculation. By utilizing the apothem and perimeter, we now possess a single formula capable of determining the area of any regular shape, regardless of its sides.